signal conditioning, data acquisition and calibration, whereas we will look into these contents. We look into the signal conditioning process. We look into one of the main component of signal conditioning, which is the operation amplifier. We will also look into the analog filters, and then signal conversion, and then we will look into the analog to digital conversion, ADC, and also DAC. Next, we will look into the data acquisition system, and lastly, calibration. So this is very important parts, okay, of this lesson. Okay, so in general, the raw output from sensors, they are non-suitable to be directly used, okay, for the end control element like the controller, or like the display. So we need to do some conversion or process to the output signal, and then the most or some several issues, okay, related to the sensor output, like for example low amplitude. Okay, this happen or true for thermocouple. So the output is in millivolts, and unusually when the output is low, and sometimes true if the output is high, the signal may be enveloped with noise. Okay, noise coming from the environment. Okay, so noise basically a systematic coming from a systematic source, whereas you can see the no, noise is basically a non-systematic coming from non-systematic source, where the pattern usually random. So there are methods how to remove the noise, and also sometimes, okay, the output is not in directly for electrical signal. We have to do, okay, some process, okay, and also in term of the how uh, to communicate between analog system and digital system. Usually, controller is basically digital system. Okay, so we need to do some conversion so that the digital part of the process can understand. So there are, okay, two concepts here, like signal conditioning. Okay, you need to understand it's basically the process of the sensor signal to adapt the signal to the requirement of the next stage in the measurement system. Whereas, for example, we need to do some amplification, and then we need to do some limitation, or we need to do some uh, noise removal, okay, or we need to do some conversion. And then signal conditioner, which is the interfacing circuit between the sensor and the data recording or process system that perform the necessary signal adaptation. Okay, signal conditioner, okay, like analog to digital converter or digital to analog converter. Okay, so that is one part of the signal conditioner system process. So we look into signal conditioning and signal conditioner. So this, as I mentioned, even mentioned in the first lesson, in the introduction, basically our sensor is a device that converts physical energy into electrical energy, and basically the sensor output, before it can be meaningful, we have to do some signal conditioning, okay, like amplification, filtering, and then next we have to adapt the output. Okay, like for example, we need to uh, communicate communicate with digital system. Need to do so in this earlier part before the end is analog, so we need to convert analog to digital, and then the process can be uh, uh, other way around, where the system want to communicate with other output, the output or the actuator which convert electrical into mechanical uh, energy, for instance. A common conditioning process like amplification, filtering, and signal conversion from resistance to voltage. We will look into that. Uh, and then protection, and also signal manipulation. Okay, signal manipulation like linearizing the output which is not non-linear into a much linear output, or like you have a AC signal and then you want to have a DC output which represent by RMS value. So those are signal manipulation. Okay. Uh, Now we look into the concept of operational amplifier. So it is a integrated circuit differential amplifier that is widely used in instrumentation circuit. So many of the instrumentation comprise of the uh, operational amplifier or op-amp component. So it is a basis of the many signal conditioning functions or module. Okay. So technically, it consists of two inputs or terminal. Okay, one terminal is a non-inverting inputs, and then the second one is a non-inverting output. And then we have a single output. Okay, this concept. Okay, the idea of operation amplifier has been well developed. So the op-amp amplify the output difference between the non-inverting output and inverting output depending on the uh, network, or depending on the wiring of circuit we put together. And the op-amp usually have a feedback, okay, feedback part, and then the element that is used uh, in the feedbacks, or in the amplification and such, we use the passive element like resistor and capacitors. Sometimes we also use the inductor. So we will look into this. We'll focus a few, okay, and the rest is just for like information. So these are the common signal conditioning, okay, in instrumentation. Okay. signal conditioning, like inverting amplifier, non-inverting amplifier, voltage follower, and so on. Right. So we look into the non-inverting amplifier here, whereas it basically operates as a constant gain multiplier. So one of the characteristic that of amplifier is that the current at the inverting uh, terminal or non-inverting input, or let's say for example I negative is the current at the non-inverting uh, input, inverting input, and then I plus is the current at the non-inverting input. The E values for both are close to zero or virtually zero, because op amp is a high has high input impedance, so it is device with high input impedance. So impedance is virtually high. So, input impedance Z in. So it takes or is consumed no current at the uh, inverting or non-inverting inputs. And then we know that V minus the potential at the uh, inverting input is minus V plus, equivalent to zero. Okay, so these two are the common relationship. So let's go through how to derive the equation on inverting amplifier. So basically the output uh, of the inverting amplifier is inverse of the input and multiply the gain, which is the ratio of RF over R1. So let's derive, or we'll show the derivation for the inverting amplifier, and then the rest will be not specifically explained, because I assume that you have uh, know the knowledge how to derive the equation for every network. So it's just in this part of the lesson we will look into some other or advanced discussion on the application. And so we start by finding the applying the current Kirchhoff current law. So I1 is the current that flow through R1 in BTV in and the non-inverting points, or the potential, or which is V minus, and then I2 is the output current that flow through the RF resistor. So we apply the Kirchhoff. I1 is equivalent to I minus plus I2. So since I2 is 0, since I minus is 0, so I1 minus I2. So we can write I1 V in minus V negative over R1, and I2 as V negative minus V out over RF. We apply the voltage, Kirchhoff voltage rule, and V minus is equivalent to V plus, or the potential at the non-inverting input. And then we see here the non-inverting input is basically connected to the ground or 0 volt potential. So V minus equivalent to 0 and V plus is equivalent to 0 volt. So we can rewrite the equation, and then finally we can derive. Okay, and basically the gain is RF over negative RF over R1, and then the V out is equivalent to negative RF over R1 multiplied with V in. Now we look into this. Hang on. Okay, so let's see here. This is inverting amplifier. Okay, specify the circuit and component for op-amp with a gain of negative 4.5. So meaning that we will try to create, okay, or try to develop this inverting amplifier by determining the suitable value for RF and R1. Okay, so so we know, okay, the equation is given here. We derive from the previous discussion. So we know that V out is equivalent to negative RF over R1 multiplied with V in. And then the gain here, this is the gain, okay, AV, okay, which is in the specification AV set as negative 4.1, negative 4.5. Okay. So we need to choose the value for RF and R1. Okay. Let's say we choose R1 equivalent to 1 ohm. Therefore, okay, uh, so therefore RF, okay, will be 4.5 ohm. So that satisfies the, okay, gain here, gain requirement. Okay, but let's say the input, let's say we set the input to 2 volt, and then we expect that from the equation the V out will be negative 4.5 multiply with 2, which is negative 9 volt.
Assalamu alaikum.
Yes.
Please, Prof, what's the meaning of, for example, when A or gain equal to salim value, like now minus 4.5. So that means Vn will be bigger or will be lower.
V out will be bigger than V in.
V out will be bigger when gain minus minus, but if it positive, that means will be lower than Vn. Yes.
No, for the negative sign represent that the signal will be invert, or negative or positive 180 degree out of phase than the input.
For example, in this case, A equal to minus 4.5, yes?
Yes.
Okay. For example, we assume that Vn equal to, for example, constant, for example, 2 volt.
Mhm.
Okay. Then what will be V out?
Negative 9. Negative 9.
In this case, so okay,
So
yes.
if you apply, i- that's the case if you apply constant value. So if you look at the magnitude, uh, okay, magnitude, especially you look at the sign, of course, negative 9 is much smaller than 2 volt. So that is true in engineering, lah, okay, point of view. Okay, but in general, okay, it can also be applied into AC signal. So let's say, for example, this AC signal, okay, vary the amplitude, okay, 2 to negative 2 volt, let's say. So let's say the 2 volt here, okay, we take the amplitude. Okay, that is actually not 100% true lah, but let's see. So if we apply the inverting amplifier, the output, okay, the amplitude will be negative 9 to 9 volt. But you see the signal is 180-degree out of phase. That's why there's a negative sign here. Okay, okay, for AC signal. Okay, but in general, this is an amplification process, right? So the idea here is we want to, okay, estimate lah the value suitable for R1 and RF if we want to create, okay, an inverting amplifier with a gain of negative 4.5. Okay. Then at the first consideration, we choose R1 to be 1 ohm and RF would be 4.5 ohm. So and then we see in the practical side, let's say, okay, the maximum amplitude of V in is 2 volt, and then the maximum, so therefore we get the maximum amplitude of V out will be negative 9 volt. Okay. So if we look back the derivation, I2 is equivalent to 0 minus V out over RF, isn't it? So if we insert there the value, okay, 9, negative 9 over 4.5, so we get 2 ampere. So you look here, so I2 is basically the current, okay, the current that the op amp, okay, have to carry at the okay, the feedback part here. So it is high, very high for an amplifier, op amp. So the amplifier usually the specification, or it can only operate at a maximum 20 milliamp. So it is not, okay, okay, basically a good choice of R1 and RF values. So the amplifier will not able to provide, okay, I2 equivalent to 2 ampere. So if we still use this combination of R1 and RF, so what happened, op amp will be you know overloaded, and then basically malfunctioning. So we need to find higher value of R1 and R2. So what you can do, okay, consider R1 equivalent in the kilo ohm, and RF, so that RF will be 4.5 kilo ohm. So if you divide RF of R1, still you get, okay, negative gain of negative 4.5. Okay, and that uh, if you use 4.5, okay, the range of current I2 will be in millivolt. Okay, so better to use a combination of resistance at kilo ohm. Okay, so you can choose 2 kilo R1 2 kilo ohm. So the combination of correct RF will be 9 kilo ohm. Okay, so that is the solution for this example. All right, so and then we have another type or another function of amplifier. Or here we have a non-inverting amplifier. So it operates as a constant gain multiplier. Okay. And whereas in this combination, V in, okay, will be in phase with V out. Okay. But the V in will be amplified by 1 plus RF over R1. Okay. And then the input impedance of the circuit equal the input impedance of the circuit equal the input impedance of the op-amp. So the input impedance Z in is here. So for op-amp, the input impedance is literally high lah, infinity ohm. So let's look at this example. Okay, design a high impedance amplifier with a gain of 42. Okay, I give direct you the answer there. Okay, equation is 1 plus RF over R1, so that's the gain. Okay, so RF will be equivalent to 41 R1. Okay, if we choose R1 equivalent to 1 kilo ohm, then it will require RF to be 41 kilo ohm. So that's the answer. Okay. Right. Next, this voltage follower, it has a unity gain, or AV is equivalent to 1. Okay. And the output will be, V out will be equivalent to V in. Okay. It is also commonly called as buffer. Okay, buffer. Whereas very high input impedance and output impedance, okay, if there is okay, there's a mismatch. This is called a mismatch between the input impedance and the output impedance. So if this is the case, if Z in is high but Z out is low, so there will be a impedance mismatch, and then will be okay, cause a loading effect. Okay. So to avoid this loading effect, we use this voltage follower, whereas okay, the output current here will not be provided by the op-amp, and the output of the I out will not consume the main input, okay, from the main input, okay, so, so that the output will always be following or same with the input. So okay, so this is a purpose of voltage follower. Then we have a summing amplifier.
Please, Prof, why we use this kind of amplifier if Vn equal to V out and without inflict the signal? So why we use it?
Okay, I have to hang on. Okay, I'll give you a simple example of it. Okay, I hope you can follow. Let's say we have a simple circuit, okay, 12 volt. Okay, in series with uh, connected to two resistor lah. Okay, we choose any value lah, 1 kilo ohm, or the other one is 1 kilo ohm. Never mind. Okay, let's say this is the output E out measure across, and this is R1. Okay, this is R2. Okay. So by calculation if we know all the value, like we know all the value, okay, so V out is basically this is V in multiply with R2 over R1 plus R2. Okay, so okay, immediately, okay, you can say the output will be 6 volt. Am I right? So the output we expect will be 6 volt. All right. Okay, so in measurement process, okay, let's say, okay, you want to measure the output, okay, not by calculation, although you know lah the actual output, okay, the actual output V out supposed to be 6 volt with this simple circuit combination. So you want to measure, okay, you want to bring a device. Okay, the common device that you can use, okay, common device you can use basically a galvanometer, or a voltmeter. Hang on. Okay, you put a galvanometer. So galvanometer, okay, is a device or voltmeter, has a shunt resistor and then the resistance of the PMMC, or for the indicator. Okay, so it has a shunt resistance and then the internal resistance of the indicator or the unsolvable circuit. So voltmeter. So you go back, or you can check later lah in the concept of galvano or voltmeter lah. You bring So you want to measure the output, you how you connect? How do you connect the device in parallel, right? A voltmeter. So this is a voltmeter. So it consists of a shunt or series, a shunt resistor in series, and then the internal resistance of Rg. Okay. So the output on the galvanometer, okay. So here, okay, in physical, okay, there will be, okay, like the display, like this, okay. And then let's say 0 to 10 volt, okay. So in ideally, okay, we okay assume that, okay, the indicator here will go 6 volt, okay, the indicator will show 6 volt. That's ideally. But what happened if we introduce this, okay, original, uh, the main current, the original main current is, let's say, I, okay. So the main current without any using any apa, what do you call, using any voltmeter, okay. So I, so basically will flow through the circuit. But okay, when we put a galvanometer or a voltmeter, so basically the voltmeter will take some current here, we call as I prime. This is I2 lah, let's say. So if this part, this input impedance Z in, okay, this is the input impedance of the device, is low. So this it will take a lot of current here, increase. Okay, increase the current here. I mean it will draw more current. Okay, low. Let's say, okay, Rg is usually very low, 10 ohm. Okay, let's say Rs we set as 100 ohm. Okay, so the internal resistance, okay, here is 100 plus 10, equivalent to 110 ohm. Okay, so we expect that, okay, with the put the voltmeter, so the output should be follow the 6 volt. But when we introduce the voltmeter here, so it will become a part of the main circuit. Okay, a part of the main circuit. So V out, the calculation, okay, will be V out equivalent to V in multiply with R2 parallel with the Z in, isn't it? Divide by R1 plus R2 parallel with Z in. So now help me, what is the value of this? What's the value? If I'm not mistaken, it is 99.09 ohm. Okay, so V out, okay, we put that like V prime lah when galvanometer, when voltmeter is attached. So so that 6 multiply 99.09 divide 1 plus 1k plus 99.09. So how, not 6, 12, sorry. So 12, what do you get? I get 1.08, is it? Am I right or I wrong? Okay, so did you get the same answer? Yeah, that 1.08. So the actual output is not 6 volt on the voltmeter. It will be 1.08 volt. It's a very high error. A very high error. Okay, because the input impedance of the voltmeter is very low. Okay, so so you see the output, okay, show on the voltmeter is actually low as compared with the actual output. Okay, so it's the voltmeter giving an error, big error. Okay, so in this case, so how to overcome one of it by using a buffer? So what you can do, okay, using the buffer here, pen, right? The buffer here, put the buffer. What's the buffer circuit like that, right? Yeah. Us. Okay. So first you look here, I plus here is literally 0 ampere. So it will never or it will not take any current from the main circuit. So I2 will always be equivalent to I. So that's one thing, this buffer circuit. Okay. Okay. And okay, how do we prove that the output using when we uh, include this buffer? So the output will be close to the actual calculation. So remember that here a buffer has Z or op amp, I say Z or input impedance is literally high, okay, infinity ohm. It may not make sense lah, but let's say you put okay what a very big value lah, 1 to 10 mega ohm. Put a very big value lah, 10 mega ohm. Okay, so when there is a op amp here, so the Z in or the input impedance of the voltmeter is no longer low. It will be Z op plus RS plus RG. So it will be 10 mega ohm plus 1110. Okay, so since this is very small as compared to 10, oh well, I close to 10 mega ohm lah. As good as 10 mega ohm. Okay, so if you calculate the V output with the using the op amp here or buffer here, so your V out now will be V in, okay, multiply with R2 parallel with Z in over R1 R2 parallel with Z in. Okay, so V n is 12. So what is the product of this? Okay, 1K with 10 mega ohm. I confirm you lah, the output will be close, okay, to 1K. It will be 999.9 ohm. Okay, 999.9 ohm divide by 999.9 ohm plus 1K. So the output will be close to 6 volt. Okay, so now with the use of the buffer, okay, it has helped you, okay, to retain, okay, the actual output, okay, to 6 volt. Right? This is like the simplest explanation I can provide. How or what's the purpose of the buffer circuit? So in many cases, you may find the voltage when you uh, put a load. So you have a, okay, for example, input, and then you put a load, and then you see a significant voltage drop. Like for example, you put a motor. Okay, so how do you retain the output? Okay, you put a buffer, one of your buffer. But motor, usually you have to use power amplifier. But this is the simplest example that I can give. Okay, I hope that you can follow. Okay, since there is no question on this explanation, right? So we proceed with summing amplifier. Summing amplifier, okay. Basically, the output voltage is the sum of the input, as given by this equation. Okay, but the summing amplifier, the output will be 180 degree out of phase, or negative lah. Okay. So in the example is the signal mixer, where you need to mix the input, okay, in that is represented by the output. And then we have a differential amplifier. where it basically the input voltage are applied simultaneously to both inverting and non-inverting, and you want to provide the subtraction of the two input, including a gain. Okay, again, this is example. Okay, good signal conditioning for thermocouple. So remember, thermocouple is two dissimilar wire connected together to make two junctions. Okay, and then this, it has a output with open terminal, and then the output is basically the EMF. So it can be the output. You can use differential amplifier to amplify okay, the signal. So differential amplifier is one option, but there's a dedicated differential amplifier. It's called as the Supplementation Amplifier. So it is a next level. It is basically a next level differential amplifier. Okay. Whereas, okay, usually, okay, come in the package. In the package, okay, there's a V uh, 2 and V1, and then the output. Okay, so the simple amplifier, usually the gain here is used as seen in this equation. Okay, actually the full equation is V out over 1 plus 2R over RP R2 over R1. Okay, V minus V2. But the above equation is when R2 is equivalent to R1. Okay, so all this R1 and R2, it basically is the internal resistance, but you can adjust the gain. Okay, adjust the gain basically by, okay, uh, applying a single external resistor RP. So you just adjust, you can adjust the gain. Okay, and it is a dedicated amplifier for instrumentation, especially a device like a thermocouple, where you can easily adjust the gain. Okay, then we have specialized op amp. Okay, like we have, you can see here is a logarithmic amplifier. Okay, so the output okay, will be linearized. Okay, according to this equation. So if you have an input, okay, is, non-linear, so the output, okay, will be linearized, can be linearized. Okay, so this one application of logarithmic amplifier. And then we have PID, okay, in especially in control circuits, where you want to apply P is the gain, PID. Gain you can apply for the gain amplifier, and then I is the integrator. So this is the integrator circuit. So basically it produces output voltage proportional to the running time integral of the input. Okay. So for example, here you have a, okay, trapezium, okay, input. Okay, so let's say from the okay time integrator is from 0 to t. Okay, so the output, okay, will be v1 multiply with the t, okay, over 2. Okay, so this, if the integrator time is from 0 to t, and so on. Okay, so this is the integrator time is depend on your setting of your system. If you want the integration, or you take the data every, like for example 1 millisecond, that will be the integration time. And we also have a differentiator circuit, consists of an input capacitor and feedback resistor. Okay, so let's say you have an input of a triangle. Okay, so the output, okay, will basically be the change of V input over change of delta T1, or the change of time. Okay, and so on, depending on the time of differentiator time. So the delta T, you be set. Okay. And also there are comparator circuit in some application. There are like Smith, I think, Smith, trigger, and so on. Based on the comparator circuit, so it useful when you want your output to follow a certain rule, where the input, when it above a certain threshold, the output will be high or alternate, and so on. I'm not going to go through this in details. Okay. Okay, come to analog filters. Basically, analog filters is to only select the certain frequency range that is desired, and then omit or remove all the range that we not desire. Okay, so there are passive and active filters. Okay, active filters employing only the passive filter using the resistor, inductor, and capacitor. But for active filter, we combine with operational amplifier. Okay, and the filter circuit can be categorized according to the type, okay, class, and order. We look into, okay, filter only in this part. We will only look into the active filter. So the common type filter, they are low pass. Okay, low pass will only allow the frequency below the cutoff frequency. Okay, FC is the cutoff frequency. So anything below will be allowed, and then above the cutoff frequency will be removed. High pass, anything is above the cutoff frequency will be allowed, and then below will be removed. Band pass, we only choose or allow the signal in between two cutoff frequency. As for band stop, is basically an invert of the band pass. We reject the frequency component between two cutoff frequencies. Okay, as seen in this example. Common analog filter like Butterworth, Chebyshev, Bessel, and Elliptic, and then these like first and second order. We look into that. Now, for example, here this is a first order low pass filter. Okay. So in this low pass filter first order, after the cutoff frequency, basically the gain will linearly decrease at a negative 20 dB per decade. For second order, the gain, okay, will reduce much faster, okay, at a much steeper slope, or negative 40 dB per decade. So the removal of the unwanted signal will be much more effective for second order band low pass filter. Similarly, we have a high pass on the other side. I mean on the cut-off frequency above the above anything above the cut-off frequency will be allowed, but below will be removed. And then the slope, okay, for first order is around 20 dB per decade, and for second order is around 40 dB per decade. Okay, so those are okay signal filter examples. And then we look into the signal conversion. Okay, so many sensor basically convert change in some physical quantity into electrical quantity. Okay. So we will look into here how the circuit are utilized to convert resistive and reactive sensor output into voltage. Okay, so the simplest method that we can use is using the voltage divider circuit, okay, by using a network of fixed resistor. So let's say we have our resistor, or we have our sensor which the resistance will change in to the physical parameter change, like heat or thermal energy or light and etc. So it is combined together with put in series with other fixed resistor, and then we apply a voltage. Okay, so the voltage drop across the sensor, okay, will be proportional to the uh, uh, proportional to the resistance value of the sensor. So this is one way how we can use conversion from resistive change into output voltage. Okay, this is example. Okay, voltage divider is more like I think one example that I show. Okay, the R, okay, this okay part can be your resistive sensitive sensor or transducer. Okay, so the output will be given by this equation, P out, or the voltage output across it. So basically the output will be proportional to the change of resistance, or either increase or decrease. Okay, R is the fixed value that we set, and of course it must be applied with the voltage supply. Right, so we have other way how to do it. This is called using a bridge, Western bridge. Let me remove. Okay. So Western bridge is also can be used to convert change of resistance to voltage. Okay. So the Western bridge consists of four arms, or four parts. Okay. Here we see R1, R2, R3, and R4, and R2 or R4 can be our sensor lah, or can be our transducer, where the resistance change. Then this Western bridge between D and C, we apply a voltage supply V, DC voltage supply, and between an AD we put a indicator or indicator, usually or a detector, usually a galvanometer. So basically, this circuit, okay, when balance mode, so there is no deflection on the detector, or the current, let's say ID here will be 0 ampere. So at balance mode here, the current that flow through the detector will be equivalent to 0 ampere. So no current, okay, no deflection. And another thing is that, okay, during the balance mode, okay, VA minus VB equivalent to 0, or in words, the voltage potential between point A and B will be equivalent to 0 volt. Okay, so point A and B is as good as an open circuit, okay, because there is no current flow, okay, in between point A and B, current equivalent to 0. Okay, so if we rearrange the circuit according to the balance mode, okay, it will resemble, okay, like this: A, B, R1, R2, R3, and R4. So this is our input. Okay, so you can find VA here and VB. So VA will be V multiplied with R1 over R1 plus R3, and VB will be V multiplied with, oh sorry, not R1, R3 here. Okay, VB will be R4. Okay, V multiplied with R4 divide with R2 plus R4. Okay, and then we know that VA minus VB equivalent to 0 volt. So VA minus VB equivalent to 0. Then VA is equivalent to VB. So we put all this into VA and VB terms into the equation here. So we get V multiplied with R3 over R1 plus R3 equivalent to V multiplied with R4 divided by R2 plus R4. Okay, so if we work out equivalent to R4, R1 plus R4, R3. Oh, I'm missing this one. 3. So finally this cancel out. So we get this term, or the ratio of R2 over R4 equals to the ratio of R1 over R3 during balance. Okay, during balance condition. Okay, so when there's let's say there is a change of R4, there will be voltage in between A and B. So that is how we can use the Wisdom bridge, okay, to convert the change of R4, the change of resistance of R4, let's say R4, okay, into output voltage, okay, between A and B. Right. But like I say, if ideally if R4 change, increase or decrease, let's say there will be potential difference between A and B. Okay. Okay, meaning that when there is a change of R4, the circuit will no longer be balanced. Okay, the circuit will no longer be balanced, and the current between that flow through the detector here will not be equivalent to 0. Okay, so how do we estimate the output between A and B? If we use a indicator here, a detector with the internal resistance of Rg, so you and galvanometer, okay, usually they comes with the internal resistance. Okay, so when we use a galvanometer as a detector, so we to find the voltage between A and B, we no longer we cannot use this relationship. Okay, this is only true when the circuit is balanced, or the current between A and B is equivalent to 0. So to find the value, the output, okay, here VAB, so we need to apply the Thevenin circuit analysis. Okay, let's see an example. Let me figure out an example. Okay, let's say in this example, so this bridge circuit have a value of R1 equivalent to R2 equivalent to R3 equivalent to 2.0 kilo ohm. R1 equivalent fixed resistor of R1, R2, R3 equivalent to 2 kilo ohm. And in this case, R4 has changed to 2.05 kilo ohm. Okay. And V is 5 volt. So if the galvanometer here, which we use as an indicator, have an internal resistance of 50 ohm. Okay. Okay, find the output voltage. Find the output voltage VAB. Okay. What is the value of VAV? Okay, we no longer can use the condition for balance circuit. Hang on. Okay. So the first step, so basically we have to construct a Thevenin circuit here, where Rg is the resistance of the galvanometer. The Thevenin resistor estimated for the circuit here, and then the Thevenin output, okay, between A and B. So we have to determine what is the value of the Thevenin circuit elements. So first step is to find the RTH or the Thevenin resistance when the galvanometer is removed lah, basically. And then we see it in between A and B. And V is short circuit. Okay, so the first step here, so our circuit will be look like this. So here we short circuit R1, R2, R3, and R4. Okay, then we have to find what is the RTH C4 here. Okay, so we can rearrange RTH. Rearranging the nodes. Okay, so it will be look like this lah if we rearrange. So the RTH it will be R1, parallel with R3 plus R2 parallel with R4. So that is basically 2K multiply with 2K multiply with 2.05K divide by 2K plus 2.05K. So Thevenin resistance will be 2.01 kilo ohm. Okay, that's the first step. Okay, so we write it down here. RTH, we got 2.01 kilo ohm. Okay. And next we go to the second step. The second step is find the Thevenin. Okay, when the galvanometer is removed. Okay, so basically V A B R1 R3 R2 and R4. So what is the VTH here? So we get the VTH is equal to VA minus VB. So equals to V multiplied with R3 over R1 plus R3 minus V multiplied with R4 over R2 plus R4. Okay, so you get 5 multiplied multiply with 2K over 2K plus 2K minus 5 multiply with 2.05K over 2K plus 2.05K. So you should get negative 30.9 millivolt. Right, so now we have our VTH is equivalent to negative 30.9 millivolt. Okay. So next, okay, we find VAB here. Okay, so VAB when we apply the detector. Okay, what is VAB when we use the detector? Because or measured by the detector is actually VTH multiply with RG over Rg plus Rth. So it will be equivalent to negative 30.9 millivolt multiply with 50 over 50 plus 2.01K. So that will be how much? So my calculation is what? So 946 microvolt, if I'm not mistaken. Maybe you may got a different answer. Okay, but that's the steps how to find the output. Okay, you cannot if you use a galvanometer with a detector, you must consider the internal resistance of the galvanometer. But if we use something else like the differential amplifier, remember differential amplifier, okay, we remove, okay, whereas, okay, we don't use the galvanometer, but we use the differential amplifier, for example, here. Okay, let's say we use a dif- differential amplifier. Okay, so there is no problem, issue, okay, because the differential amplifier has a very high impedance input. Okay, so the uh, condition here can be used, or the balance mode can be used if if you apply differential amplifier. Okay, so and next is the reactive sensor signal conditioning, whereas you in determine or measuring the change of other passive element like capacitance or inductors, they are passive, but uh, basically they uh, work on AC level or AC signals. So we can also use the um, bridge, similar to Wisdom bridge, to find the to convert the capacitance or inductance change into output voltage. Okay. Next, we look into the analog digital conversion. Let's take a 10 minutes break for prayer. So we will resume at 4:30. Okay, we continue our class here. Okay, so so this is the uh, discussion on analog to digital conversion. Basically, it's a process where to convert from either digital analog to digital or digital to analog. So we will look into that, and first we look into the analog digital conversion, which turns the signal from analog signal into binary. So the ADC operation can basically can be divided into two parts, in the sampling and the quantization. Uh, so we all know that digital or analog signal is continuous signal, but when you convert into digital information, so the magnitude will be represented in discrete step. So there are some of the part in the analog to digital circuit is like the sample and holes, which produce the whole the voltage value at a certain time, so that the conversion then the ADC will lose the conversion time, the conversion process. So during basically the quantization is a process where the analog value at discrete time convert into discrete binary value. So the ADC uses the integer value from list of finite list of value to represent each analog sample. So the integer value is in the list represent a fraction of the full scale range of the ADC. Full scale will be determined by the reference. Okay, these are the figure, whereas how the ADC process from input, and then the potential is held by a sampling and hold circuit, and there's a ADC and then the quantization circuit, and then we get have the output. Okay, so the process, first important part of the ADT converter, there must be a voltage current converter. So basically, in the voltage current converter, the current is applied to a summing junction at the input of the op amp, and then the high impedance at the input of the op amp, allowing that the IR or the output current equal to the input current. So because the current input or current at the non-inverting input virtually 0 ampere, because of the high impedance. Okay. Therefore, cause the voltage drop across the resistor, which is proportional to the current. Okay. So the voltage drop is the input of the AD converter, so which will be used by the ND converter, and then the basically the magnitude of the current converter or the gain will depend on the selection of the resistor value. Like for example, the magnitude of 10 and the magnitude of 100 and the magnitude of 1000 can be done, okay, by selecting or changing the channel. Or now we look into the concept of digital to analog conversion. Okay, we basically look first at the digital to analog conversion. The digital analog conversion basically, okay, we have digital inputs, okay, to produce an as output, analog output, and the DAC basically operate at the reference voltage. So the output will never be more than the reference value. Okay, so for example, here we have a binary information. Want to convert to analog voltage. So for example, 1, 1, 1, 1, 1, 1. Okay, so the conversion to the output can be, we can use this equation. Okay, so basically the output in analog equal to the reference voltage multiply, okay, multiply the summation of uh, bit value, okay, at each bit place multiply with its factor. Okay, for example, bit place B1. So in this formula, the bit place B1 is on the at the left most, multiply with its factor, which is 2 to the power of -1, which is the first bit place, okay, from the left. Okay, plus to the next bit place, okay, the bit value in binary, multiply with the factor 2 to the power of -2, and so on. Okay. So for example, okay, 4-bit word with 1 or let's say 4-bit word. Okay, what is the output if the all the bit is set to 1, 1, 1, 1, 1. Okay, so VR will be multiplied with the sum of the product. Okay, bit place, every value of the bit value, for every bit place, the bit value multiplied with its factor. Okay, we sum of it, and then we get 0.9375 VR. Okay, so the output, okay, will depend, okay, on the reference. So here we can see that the maximum output, okay, will never be more than the reference value. Or we can use this formula. Okay, this is another formula that you can use. Okay. First, but using the formula, you need to convert the binary value, binary information value into decimal value, okay, and divide by 2 to the power n. N is the number of bit places, okay, and multiply with the small n, multiply with VR, or the reference value. Okay, so for example, 8-bit converter, okay, with 5-volt reference has an input of 101001112. Okay, so the digital of analog converter have a reference voltage of 5 volts, and it has a 8-bit input. Okay, we need to estimate the output. So if the input is 1010011112, when we apply, okay, the conversion, So we get that in decimal value 167. Divide by 2 to the power of 8. Okay, the bit place multiply bit 5, we get 3.2617. Okay, that's okay. So next, we use okay. What if the output more 10 bit DAC with a 10 volt reference? If the input is 00101101001, okay, we can use the both. Let's see. We use the first formula. Okay, if we use the first formula, uh, requiring to sum all the uh, value of every bit place, binary multiply with its factor, okay, and then sum all the value. So we get 1.067 or 1.77 volt. If you use the this formula, so yeah, you can suppose to get the same answer. What is the digital input needed to get an analog 5.625? Okay, but before that, okay, what is the advantage of use this and this? If you use this formula, okay, you need to convert the binary value into decimal. So decimal value. But sometimes your calculator can only take a limited number of bit places. Okay, like 16 bit or other than 20 bit, for example. Okay, beyond 16 bit you cannot calculate. So if that is not possible, you have to use the first equation to find the output voltage. And then what is the output if what is the digital input when the analog is output is 5.625? So let's say we retain the VR to 10 volt. So use this formula, the second formula. Okay, we get the decimal value 576, and then the equivalent binary value is 1001000000. Okay, so this is an exercise. Okay, when all our inputs are high, what is the reference voltage? Okay, find the reference voltage. Okay, we can use the second formula. Okay, we need to find what is the VR. What is the VR? Use this formula. But the output is 8 volt. So first step, okay, is to convert the binary input 4 bit, which is set all high. So meaning that the input is 1111. So we convert that into decimal value, we get 15. Okay, so we use in the formula 8 equivalent to 15 over 2 to the power of 4. 4 because 4 bit place multiply with VR. So VR we get 8.53 volt. And then resolution, basically the smallest possible change, okay, of the digital to analog converter. So for digital analog converter, so the smaller the resolution means that the higher, this possible change in terms of the delta out is smaller, means that the resolution is higher, or the quality of the conversion will be much better. Okay, so for example, 5-bit digital analog converter with 10-volt reference. Okay, we provide the delta out, we get the around 312.5 millivolt. But if we go for 10-bit, we get smaller value, which is delta out smaller value is 9.7 millivolt. So if we compare the output, the performance, the higher bit ADC will be much better. Okay, so in this example, okay, so this example show us a control valve, which is uh, controlled by a microcontroller. Okay, so a microcontroller control a valve through a digital analog converter. Okay, hang on. It has a reference voltage. AVR and V out. So the output, the analog output, okay, is used by uh, a, a, a motor, okay, which will manipulate the opening, okay, of a valve. So the statement is that opening here the opening of a valve from 0 to 100%, it will be between 0 to 10 volt. Okay. So the output is from 0 to 10 volt, whereas the opening is 0 to 100%. Okay. So the input of the valve, okay, it can be water flow. So the first question is to require what is the VR value. So immediately we can use this equation. VR multiply with n divide by 2 to the power of n. Okay. And this is the 8-bit, okay, 8-bit DAC. So if output is 10 volt, means that the input or the output from the microcontroller will be all high for every all high for the bit output. So n is basically the you need to convert the 1111 to the decimal value, right? So VR is basically equivalent to the power of n multiplied V out divided by n. Okay, so 2 to the power of 8 multiplied with 10, n for 1111 Yes, I think supposed to be 255 if not mistaken. Okay, 255. 2 to the power 8 is 256. So the reference is 10.039 volt. Okay. And then the second one, what is the percentage of valve opening for 1 bit change in the input? Okay. So it want to know, okay, if 111111, okay, basically proportional to 100% of opening, and then I mean at 10 at 100%, the output level is 10 volt. So what is let's say 1 bit change, say 11111110. So what is this percent? Okay, percent, and then the voltage here, E out 1, let's say. Let's say V out 1 or V out 2 lah. Okay. So the percentage you can find by, okay, find this value V out 2 minus the V max, or at 10 volt here, 10 volt, divide by 10 volt, multiply with 100. So you get the percent. So what is this value? Can use this formula for V out 2. So V out 2 supposed to be 10 multiply 039, multiply this value in decimal. So that value in decimal is 2254 divide by 256. So you get is it? So you get 9.961. So the percentage is 9.961% minus 10 divide by 10. So you get what? Okay, so yeah, you get 0.392%. Okay, so that's the answer for this tutorial. Okay, I think that's for the lecture is that's all. Okay, so